This week we'll be covering stretching, movement prep, and warming up. Before we begin, it's important for us to sort of unpack some of the concepts that we're going to be discussing this week. And when we talk about sort of warming up, stretching, flexibility, the whole goal of warming up is to prepare the tissues to move as it relates to exercise, certainly performance, athletics. But some of the things that are often overlooked are some of the mechanisms and some of the structure that goes into or what makes up our own, really our muscles, our connective tissue, and what we call our fascial system. It's important to sort of dive into this a little bit more, especially as the industry over the last 20 years and movement science over the last 20 years has really started to look at tension and integrity, looking at a full structure. So let's look at this slide here. You see tensegrity is a concept that equals tension and integrity. And tensegrity was a term that was coined by a gentleman by the name of Buckminster Fuller. I'll put some photos in here of a variety of structures that he was responsible for in the 50s and 60s. And essentially, it was a coined phrase, so you can see tensegrity is made up of tension and integrity, and that's how you get that word. So tension is simply the act of stretching or straining. So that woman there doing that yoga pose, she's actually stretching the anterior aspect of her upper trunk. And you can certainly stretch to the point of a strain where you can actually stretch too much and cause an injury and or a muscle tear. Now, the term integrity means sound, unimpaired, or perfect condition. So when we combine these two terms, we get the definition for tensegrity, which is tensional integrity. So sound, unimpaired, or perfect tension, also known as floating compression, is a structural principle based on the use of isolated components in compression inside of a net continuous tension, in such a way that the compressed members, usually bars or struts, do not touch each other, and the pre-stress tension members, usually cables or tendons, delineate the system spatially. So, look at the suspension bridge. The suspension bridge is not fully a tensegritis model, but it comes pretty darn close. But there is structure sort of holding on to each other. But that the tension is actually disseminated across the vertical columns on the Golden Gate Bridge, and the structure itself, the road, is held up by equally displaced tension along those big cable columns, along those big cables that run from the entire span of those vertical columns. So there's an example of tension in use. What's a little bit different about tensegrity is saying it's equally displaced. So that the system is equally spread out, meaning that the tension is distributed equally, creating structure. So in the next slide video, I'm going to show you a tensegrity model, and we're going to unpack that a little bit. Okay, class, so I wanted to just show and demonstrate to you the concept of tensegrity using a tensegrity model. So I have my trusty handy tensegrity model here. So I want you to look at this. So this is essentially a bunch of wooden struts that's got these black rubber bands that is holding it together. But I want you to look at it from a few different angles here as I turn it around. Notice that the struts do not touch each other. Okay, everyone can kind of see that. I've moved it around a few different ways. The struts do not touch each other. And the rubber bands go around the ends, and it's got these little fancy end caps on there. That's just basically the dowels have a little slit, and the rubber bands sort of track on the outside. So this is a perfect example of tensegrity in play. And what's critically important to understand here, as I just want to get in frame here a little bit better, is that there is equally distributed amounts of tension throughout this vis-a-vis the rubber bands, but And the structure is held together by the tension that's equally distributed through the stiff, rigid columns. And consider that since the columns, the sticks don't touch in any way, how is it holding itself together? Well, through this tension, right? I want you to think about the human body. Technically, bones do not touch. Technically, they should be sort of held in place. Well, in fact, when you see a skeleton that's held together just as sort of like an anatomical skeleton in a medical class, it is actually held together with screws. So the bones themselves do not stick together. They don't have any contact point. There's no way for those bones to stay together. So what they do is they put screws in it so you can just look at the skeleton. But that's deceptive, because what is actually holding the bones in place? The tension of the connective tissue. So muscles, tendons, to some extent ligaments also hold bones in place. And this is all tension. And tension equally you can have too much tension or too little tension. Too much tension might be tightness. Too little tension might be joint laxity, hypermobility, excessive flexibility. So there is a balance. There's a yin-yang with function and flexibility versus stability and control of a joint. We don't want joints overly stiff or tight. That can cause problems. We don't want joints excessively mobile, beyond normal range of motion, because that can also cause problems such as dislocation, etc. So what does that have to do with this? Well, let's talk about this. So right now you can see this relatively makes I don't know what size this is, but there's multiple sides here, but it makes a really stable shape. Now, interestingly, what happens if the tension changes? So let's just say, I'm going to give you a close-up here. I'm going to take this band, and I'm going to grab it with my fingers, and I'm going to shorten it. Let me actually pull it back this way. I'm going to shorten it from the back side. I hope you can see this. But when I pinch one of the rubber bands, and what I should do is I should probably pin it together. But you can see I've actually held the rubber band together. Let me demonstrate how I'm doing that. So I'm basically taking some of that rubber band and I'm basically bringing these two pieces closer together. What you start to notice is that the shape changes a little bit. Now the tension now is not equally disseminated or distributed across the whole structure. So if I was to have you now, even though it's sitting here, you can see now it's actually slightly at an angle, it's less stable. And if I was to have you put some pressure on this, it would actually start to collapse much more easily. Now I restore the equal amount of tension and I make sure that it's pretty stable. I can obviously I can smash it if I really want because it is just rubber bands and sticks, but the structure itself is held together. Now imagine something that is a lot more rigid like steel and steel beams, etc. So you can imagine how that could be a very, very, as long as tension is equally distributed around the structure, that could be a really powerful structure. And I'm going to show you some videos or some photos at least of other tensegrity models that don't have any real joints. They're just held together with tension. But the big takeaway for this is think about the human body as a tensegrity model. It just simply means that we have tension that holds our structure together. It's connective tissue, it's fascia, it's muscles, it's tendons, and to some extent it's ligaments. And when we do work that makes us tight in an area, that creates an imbalance in the tension, length-tension relationship. And that can cause all sorts of problems to our structure. So just keep that in mind. We're going to continue on with this lecture, but I wanted to take time to explain to you what the tensegrity model is and what it looks like. So here's some other pictures of tensegrity dynamics, or tensegrity models, so to speak. These are bridges, but look at this bridge to the left, on the lower left, at the bottom of the slide. Look at all the tension suspension that's happening there. So without those supported struts and equal dissemination, and dissemination just means that force is being moved around through the tension wires. and force is being equally distributed along those wires, being sort of forced out, so to speak. That tension is equally distributed is probably a better term for that. Dissemination means distributed. The force and the tension is equally distributed amongst that entire structure, keeping that essentially bridge from falling down. On the right-hand side, lower right-hand side, you see a similar model. You see just these are very, aesthetically very, attractive or beautiful bridges, right, from a pure architectural standpoint, but they have to function. And you see the tension is being disseminated or distributed out through those two vertical columns, similar to the top bridge here. You can see in the suspension bridge, we've got two suspenders. Those are going to be the vertical red beams, and they're grounded or they're held into place by cement at the bottom of the water that they're traveling, or excuse me, if this is a river as an example or a bay. And then they got the vertical columns, the suspenders under tension, and then at each end we have anchor points, and then the cables run across, and then we have suspension under the tension of the cables. So there's really equal distribution of force being pulled, very similar to the human body. And it's important to think about the human body as more of a tension dynamic versus anything else, especially when we talk about movement and understanding how movement should occur optimally when it comes to exercise and working out. Now let's dig a little deeper here. Now we see tensegrity, tension and integrity inside the human body. So historically, when we dissect cadavers, and we've done a lot of dissections over the years to kind of understand the human body, obviously from the organs, from the cellular level, looking under microscopes, all anatomically looking at sort of the big picture, we've historically had a view that is parts driven. And many of you probably are experiencing that too when you work out. You say, hey, I'm going to work out my biceps today. Monday's chest and tris. That's what I'm going to focus on. So you're used to the part conversation. Well, over the last 20, 25 years, we have seen a shift, what we call the paradigm shift, a change in the way of thinking about human movement as well as human anatomy from a movement perspective. So you see muscles on the left-hand side. You see these anatomical drawings with these blue bands. We have what are identified on the upper left as the spiral line, the arm line in the middle, superficial front line, the deep front line in the lower left, the lateral line in the middle on the left, and then the superficial back line on the lower right of the left-hand photo. Those connections or those lines have come about because instead of dissecting muscles, saying I want to dissect the calf and I want to take the calf off the cadaver and I want to look at it, where it attaches and where it inserts, we're keeping what are called the fascial connections intact. Now, fascia, understand, is collagenous fiber. It's like collagen matrix. It's like a mixture of a variety of collagen and other substrates that actually connect tissue to tissue and connect every living cell in the body to other cells. And when and I'm going to play a video here next for you called Fascia in Motion, or it's called Strolling Under the Skin. And it's a remarkable video. The next video, I'm going to put it up and post it in here for you. Shows you what it looks like when we take a microscope and we go under the skin and we can see all these fascial connections in actual living tissue. They're covered in fluid. They transmit information before the muscles move. So the fascial system is integral to human movement. And for the first time in forever, we've started dissecting correctly to keep these what we call fascial lines, intact. And similar to the chicken breast or a piece of chicken, there's like this white material. When you pull the fat off or the skin off the chicken, you'll notice that there's like a white kind of rigid material. Well, that's similar to what fascia is. It's this rigid material that has some play in it. It's not like hard. It's not a bone, but it's this very durable material that has a lot of information that translates between the electrical system of the nervous system and the actual mechanical or the chemical system of muscles and chemical reactions that cause muscular contraction. Now, on the upper right-hand side, you might say, oh, that's gross. That's actual dissections of the various superficial lines connected. And in those long ones are actually the legs. That's actually in the middle there. That's the superficial back line, going all the way up to the brow ridge. And we're going to talk about that when we break out into lab today. Now, the question on the lower right-hand side, are there really 600 muscles or only one muscle in 600 fascial pockets? Because we're discovering that those blue lines on the left, there's about 14 of these now that we've discovered. These are only 6. And depending on how we dissect, we see these connective tissues that are beyond just a single muscle. They're multiple muscles that are connected together. So I want you to think more of the human body, in particular from a movement standpoint, from a fitness standpoint. At the bottom there, you say we are basically just a connected bundle of, or bags of cells. And that's really what we are. So the question always comes up is, if we're all connected, why do we teach learning muscles? Why do we teach parts? And that comes from that old view of let's deconstruct, take it apart so we can understand it. But we've sort of forgotten to put it back together and look at it holistically. And so that's what we're finally doing now in the last 20 years. And it's created what we call a paradigm shift, a shift in the way we're thinking about movement. So movement matters, and good quality movement, moving through full ranges of motion matters, and even moving in some of those fascial lines matters. But what I wanted to do today was talk a little bit more about sort of stretching and creating flexibility, because if you have too much tension in one group of muscles, you're going to have weakness in the opposing group of muscles. So a common example would be hamstrings are tight, hip flexors are tight, rectus abdominis or abdominals are probably weak, and glutes are weak. There's always a relationship between something overly tight and something underly active. And our job as kinesiologists is to figure out what is that relationship, and what can I do as a coach, trainer, physical therapist, athletic trainer, what can I do to help improve the quality of the tissue so that the tension is equally distributed amongst the entire structure. If the tension is equally distributed, the entire structure will perform better and move better. So how can we release tightness? Now, one of the things we can do is called self-myofascial release. This is a type of stretching, and that's a fancy term for myofascial release, which is the fancy term for massage. So massage therapy is called myofascial release. I know everyone's gotten a massage at some point, and you love that when something feels tight and someone can push on it. Yes, it hurts, but it's got that sensation of hurt so good. That is the massage. Now, self-myofascial massage, myofascial release, is you see that Tony Parker, who's a former NBA player, sometimes you see now LeBron James also doing this. They're foam rolling on a piece of styrofoam or some piece of equipment, rolling their tissue. So you might think, well, why are they doing that? They're actually warming up. They're actually increasing that range of motion through self-myofascial release, or self-compression is essentially what it comes down to. Now, some other types of stretching that we can do. Static stretching. That's where we hold a stretch. So you see that woman at the very bottom there on the grass. She's grabbing her toes. She's stretching out her hamstrings, her lower back, her mid back, not quite her head. Her head is flexed backwards, right? If she wants to stretch out her neck, she should let her head come forward. And then she's fully stretching out that superficial back line, which we're going to demonstrate in our lab today. Another type of stretching is dynamic, and I'm going to give you some videos to watch on dynamic stretching. Dynamic stretching is the best because it actually recreates a lot of the movements that you're going to be doing in athletics. And so you'll notice that if you've played sports more recently, or you've worked with a progressive physical therapist, trainer, athletic trainer, they are doing dynamic stretching. They're not holding stretches as a static stretch. Now, static stretching does work, but static stretching may not be the best when it comes to preparing, at least in the exercise science research. It's not the best to prepare an individual to move. Some other stretches include ballistic stretching, which is more bouncing. We don't typically do that. And then PNF, which stands for proprioceptive neuromuscular facilitation. And that's a series of stretches that you would do with a clinician or a personal trainer, where they're actually offering you resistance, you're pushing into them, and then you're relaxing and they're actually able to stretch you further. PNF is actually the best type of stretching to do, but it requires a partner to do it with you. So in general, what are the overall benefits of overall flexibility and stretching, or improving flexibility and stretching? Helps to restore that joint tension, what has historically been known as muscle balance. It increases joint range of motion. It decreases excessive tension of muscles, relieves joint stress, may improve the extensibility of the musculotendinous junction, basically the connection points of muscles as they transition into tendons, which is all connective tissue, and it allows us to maintain normal function and length of muscle. So flexibility and stretching, whether it's self-myofascial release or even static stretching, is important for overall length of maintaining functional length of all muscles, which overall will improve optimum neuromuscular efficiency, meaning how does the body recruit muscles? How does the body, when it pulls against one group of muscles, does it have the amount of resistant tension on the opposing muscle groups so that we can function properly, which ultimately translates to improving function and performance. Now, I want to specifically talk about self-myofascial release because this is what we're going to have you do in lab, in discussion lab. So what is self-myofascial release? What does it actually do? Well, it actually improves the range of motion at the joints, meaning we're going to foam roll a muscle, and if we foam roll the quadriceps, so your quad, the front part of your thigh, if we roll that, it should increase the range of motion at the hip, because that's one of the joints it crosses, as well as the knee. That's another joint that it crosses. The pec, as an example, your chest. If I foam roll my pec, it should help to increase the range of motion at my shoulder. It decreases muscle electrical activity. So that compression, pushing on the muscle, reduces the electrical activity. It turns it off. It also decreases pain pressure sensitivity. So over time, self-myofascial release can improve, or it doesn't hurt as much. Your pain tolerance decreases. Allows you to actually tolerate more pain compression. It decreases delayed onset muscle soreness from vigorous exercise. So when you're first working out, you're like, oh no, I'm going to get super sore. Well, if you foam roll, in the exercise science literature, it actually demonstrates that it's going to reduce that muscle soreness. So if you're a personal trainer and your client is worried about getting overly sore from their first few workouts, you better be foam rolling with them, because that has been scientifically proven to decrease delayed onset muscle soreness from, new workouts. Now, the greatest improvements in flexibility happens when you combine self-myofascial release, foam rolling, and stretching. So personal trainers in the room, self-myofascial release is great, but we also want to stretch them to help create that greater synergy of increased range of motion. Now, what's the best time to foam roll? Great question. Well, if it increases range of motion, we should probably foam roll before we work out, especially if we have a client or you are someone that has some restriction. I want to loosen up that restriction. I want you to foam roll before your workout. Now, you want to hold on the sensitive spots, and we're going to demonstrate this in discussion lab. And you want to hold the foam roller on those sensitive spots for at least 60 seconds. And you want to facilitate rolling through the areas of muscle that you're going to be focusing on. So if it's a lower body day, maybe I'm going to focus a little bit more on lower body, quads, hamstrings, glutes. If it's an upper body day, maybe I focus on pecs, shoulders, latissimus dorsi. And if you're doing full body, maybe you do the big muscle groups that are going to be responsible for that workout. Now, we like static stretching because it's easy. You can do it to yourself. So there's not really any cost. I don't need a piece of equipment to do stretching. It helps to have a stretch strap, but the reality is you don't need a stretch strap. You can do some stretching on your own. It's certainly effective, at least increasing range of motion temporarily. It may not be the best. What we know in the research is it's not best to do some stretching before you do explosive lifting. So I don't want to do static stretching before I'm going to be explosive. doing Olympic lifts, Olympic cleans. That's why dynamic stretching, which we'll get into here in the next slide, is going to be our optimal. It's going to be our optimal dynamics, or optimal stretching protocol. Excuse me. Stretching is a game of opposites. So if my hamstrings need to be, my quadriceps or my hamstrings are tight, I'm going to pull to the opposite direction of where the hamstrings bring me. My hamstrings bring my hips backwards. They do hip extension. So I want to bring myself into what we call hip flexion. So that woman at the bottom, you see both of them pulling on their hamstrings. In the woman where it says hamstring muscle, the drawing, she's pulling her quadricep towards her chest. That's stretching out the hamstring muscle. So it's a game of opposites. You typically want to repeat 2 to 3 times, holding each stretch for 60 seconds. Now, the question is, can you stretch too much? Absolutely. Hypermobility, too flexible, is potentially very, very destructive in that the body can't decelerate movement. It can't slow a movement down. So overall strength, adding a little bit of, resistance towards an end range of motion vis-a-vis building some muscle up is really helpful for someone who's overly flexible. Now, dynamic stretching is fantastic. It literally is the best way to stretch, and it allows you to prepare the body by moving coordinated muscles synergy. It increases neural coordination. So the nervous system has to turn on, the muscles get warmed up, they become more flexible because of your core temperature is increasing. We can do dynamic stretching on our hamstrings, quads, glutes, or piriformis, another part of the glute. I'm going to demonstrate, I'm going to add some videos here that show you some of these other stretches. The greatest stretch in the world, toy soldier, leg swings, high knees, skipping, bounding, butt kickers, heel walks, lunging with an overhead reach, over, under, karaoke, inchworm. And then we have a whole bunch of animal things, which we've already seen in some of our videos, but the bear walk, out of sync versus in sync, crab walks, frogs, orangutan, lion, alligator, crocodile, etc., etc. And finally, if you have any questions, please use the discussion board. I'm happy to answer any questions that I can, any questions that you have about this module. All right, so move on to some of the other videos and check out the rest of this